Okay, we are about to dive into one of the most just absolutely mind-bending ideas in all of physics. We're talking about a connection that seems to completely defy logic by stretching across time itself. So here's the question, and it sounds like it's straight out of science fiction, right? Can a particle that was measured and destroyed, I mean, it is completely gone from the universe, somehow become fundamentally connected to a brand new particle that hasn't even been created yet?
Well, the answer, and this is what's so wild, is yes. A resounding yes. And this isn't just some thought experiment, it's been proven in a lab. So, we're going to break down exactly how scientists pulled off this little bit of temporal magic. But first, we need to understand the tools they used.
So let's start with a concept that even Einstein himself found, well, deeply unsettling. It's a kind of quantum handshake that's really the foundation for everything that's about to follow. This, of course, is quantum entanglement. You've probably heard of it. Imagine you create two particles together. They become linked. So if you measure a property of one, say its spin, you instantly know the spin of the other, even if it's on the other side of the galaxy. It's this perfect, instantaneous correlation that Einstein famously called spooky action at a distance.
Right, but that's the core of our puzzle. See, normal entanglement needs a shared origin story. So how on earth could you possibly entangle two particles, let's call them particle 1 and particle 4, if they come from totally separate places, and in our case, never even exist in the same moment? The answer is this absolutely brilliant technique called entanglement swapping. The best way to think of it is like a quantum relay race. The runner at the starting line and the final anchor never actually have to meet. You just need the runners in the middle to successfully pass the baton. Okay, so here's how that relay race works. First, you create two completely independent entangled pairs. So particle 1 is linked to 2 and particle 3 is linked to 4. At this point, there's absolutely no connection between 1 and 4. Then, you take those middle particles, 2 and 3, and you bring them together for a very specific measurement. And this is the magic part. The moment you do that, particles 1 and 4, which have never seen each other, instantly become entangled. Now, the key here is that this isn't just any measurement. It's called a Bell's state measurement, or BSM. It basically forces particles 2 and 3 to reveal which of the 4 possible ways they are entangled with each other. And by forcing that answer, you establish a brand new, specific entangled link between the outsiders, 1 and 4. The BSM is the catalyst. It's the moment the baton is officially passed. So with this incredibly powerful tool, physicists started to push the limits. First, they went for distance across space. And then they did something even more daring. They stretched it across time itself. You know, at first, the big challenge was just proving this swapping thing wasn't just a neat little trick you could do on a lab bench. Could you really create that spooky connection between particles that had no shared history and were actually far, far apart? And the progress was just stunningly fast. In 1998, we had the first successful swap, a huge landmark. Then, in 2012, things got really weird. A delayed choice experiment hinted that a future event could actually define a past reality. And then, just 1 year later in 2013, they made the final leap, entangling two photons that literally never existed at the same time. This idea is at the heart of that 2012 experiment. It suggests something that just feels wrong, like it's violating causality. The idea is that the measurement you choose to make in the future on those middle particles seems to reach back in time and define the relationship between the particles that were already measured and are long gone. Now, this is a really important point. It's not about changing the past. The original measurements, what happened to particles 1 and 4, are recorded. That data doesn't change. In fact, if you look at that old data, it looks totally random. But then, later, when the results from the future measurement come in, they act like a key or a cipher. When you use that key to sort the old data, boom, the hidden spooky correlations suddenly appear. The future just gives you the secret decoder ring to unlock a quantum pattern that was there all along. And that incredible insight is what paves the way for the grand finale. This is where we put all the pieces together and finally solve that impossible puzzle we started with. So that brings us back to the ultimate question. We're not just talking about delaying a measurement anymore. We're talking about a photon that is measured, absorbed, and destroyed. It's gone, poof, and linking it to another photon that is created at a much later time. I mean, how is that even possible? Okay, let's walk through this brilliant 2013 experiment. At time 0, the team creates an entangled pair, 1 and 2. Photon 1 is immediately measured, destroying it. It's gone. Meanwhile, its partner, photon 2, is sent on a little trip through a fiber optic cable, delaying it by 105 nanoseconds. Exactly 105 nanoseconds later, a totally new entangled pair, 3 and 4, is created. And just as photon 3 is born, the delayed photon 2 from the past arrives to meet it. They perform that special Bell state measurement on them, and the result is just staggering. The data, the measurement record of the long-dead photon 1, is now verifiably entangled with the brand-new live photon 4.
So what is going on here? How does this work? Well, the secret is that photon 2 acts as a perfect quantum messenger. You can think of it as a temporary quantum memory. It faithfully carries the information about its entanglement with photon 1 forward through time. It preserves that quantum relationship. So when it meets photon 3, the BSM isn't linking the particles themselves, it's linking their correlations. The information from the past gets swapped onto a particle in the present.
And believe it or not, this is way more than just a fascinating, mind-bending experiment. This principle of connecting things that don't exist at the same time is actually the cornerstone of a technology that is poised to completely reshape our world. Because the future of truly secure communication, of distributed quantum computing, all of it depends on building a quantum internet. And you simply cannot build that network without mastering entanglement swapping across time. See, the biggest problem for a quantum internet is that photons get lost or absorbed in long optical fibers. So to get around that, we need things called quantum repeaters. And what is a quantum repeater? It's literally an entanglement swapping engine. It sits in the middle and tries to entangle a photon from its left with one from its right. But these attempts don't always work, so the repeater has to store a successful entanglement from one side and just wait, maybe for milliseconds, until the other side succeeds too, and then it performs the swap between photons that were never created at the same time. Of course, this all hinges on developing really good quantum memories to hold that fragile information. Simple fiber optic loops, like in the 2013 experiment, can only hold a photon for a few microseconds. But now, researchers are using things like clouds of ultra-cold atoms or tiny perfect defects in diamonds to store these quantum states for milliseconds or even seconds. That's more than enough time to coordinate these swaps across a future global network. What this all means is that we are literally engineering a new kind of reality. Those clear, classical lines we've always drawn between space and time, between the past and the present, they're starting to blur. We are learning how to weave connections through space-time itself, using the thread of quantum entanglement. The ability to link information across time just opens up entirely new worlds for communication and computing. It really forces us to rethink the nature of time itself, and it leaves us with one absolutely thrilling question. Now that we know how to stitch the past to the future, what will we connect next?